Welcome to lecture 15 of Rob 101. We are going to cover the last part of chapter 10, third part of vector spaces. Today's lecture is about range, null spaces, and rank and nullity theorem. So the objective is the same as the last lecture in chapter 10. We want to cover some essential topics in linear algebra. Specifically today, we talk about the range of a matrix, and we want to establish some connection with the column space and null space of a matrix. We want to put everything together to get a common understanding of these topics in one place. The first thing we need to do that will help us to build a better intuition of how to think about a problem is when we think about a matrix as a function or a map. So the function view of a matrix, it leads to two important subspaces. One is the null space of a matrix, and the second one is the range of that matrix. So what do I mean by the function view? So you probably know that a function is something like f of x. For example, x squared plus 1. This is a function. X, for example, here can be a real number. So if I, for example, evaluate f of 2, this will be 5. So my function f takes any real number and maps it to another real number. So mathematically, you can write this, f colon, let me write it here. So f is the notation, the symbol I'm using for my map or function. This is what we call domain of the function. Domain is where it takes its inputs, the arguments. And this is what we call the range of the function. Range is basically the set that the outputs can live there. They belong to that area. Now, it happens to be the case that domain and range are the same. They don't have to be, right? Now, suppose now we're talking about, instead of a linear equation or an arbitrary equation, specifically, we're talking about our matrix A. A is an n by m matrix, which means A can be multiplied by a vector, and it will give you, say, another vector like y or b. So if A is n by m, we know that from matrix multiplication rule, x is m by 1, and y is n by 1. So in other words, A, you can think about it as a function that takes m vectors. M vectors, they have real numbers as their entries, and then map them to n vectors. There is nothing wrong with thinking about this matrix as a function like this, because it perfectly fits into definition of a function. So that's what I mean when we think about a matrix as a map or function. It takes an m vector x and then turn it into n vector y. So we define our function, you could call it f of x, is just a times x. So a times x, f of x, or you could call it y, it doesn't matter, you can choose your arbitrary symbol. That belongs to Rn. However, x belongs to Rm, right? So this is a map from m-dimensional space, Rm, to Rn. So the definition for this input, output, and particularly the subspaces that comes out of this way of thinking about the matrix is first the null space. The null space of a matrix, we had a brief encounter with that in a few lectures ago, is the set of all vectors that if we multiply our matrix by that vector, the result is 0. In other words, the null space is a set of all vectors that satisfies the homogeneous linear equation. And that's what we call the null space. It produces the null vector. The null space is a space of all the vectors that when we multiply A by those vectors, it gives us the null vector. Okay? Now, we did show that null space is a subspace, but we're going to show it again today. Now, another one is the range. Similarly, the way we define the previous set, now we can define another set that is set of all vectors, now this time Rn, y in Rn, such that y is the outcome of multiplying A by x. So whatever that might be, take all x values and vectors in Rm, and then you can calculate the y for each of them, put them in a set. It's going to be a set of n vectors. That's called the range of A. Basically, how much A, this matrix, can cover in the output set in Rn, right? That's the range of N. Like you might have heard of in boxing, for example. What's the range of a boxer, right? When you stand somewhere, you can punch, your reach, your range. This is exactly that. That's the meaning. How much you can cover based on where you stand. All the possibilities, that's the set we call range. Now, here, for this particular example A, we can calculate it that y is A times x. So that's the reach or range of this matrix. But we don't use reach, we use range. Now, we define our two subspaces, but we need to be able to calculate them. And that's what's important in practice. You will do it in your homework as well. For example, here I am asking to calculate the null space of A1. This is a 2x3 matrix. If I want to write this as a map, what is the first part? What is the domain? R2. domain is where I can multiply A by X. So it's R3. What is the range? Now, in the most general case, it's not the range of A. We need to calculate it, but at most, it's going to be like this, right? Now, it's not going to be entire R2. That's the problem, right? It's going to be a subset of R2. It could be, at the most complete or extreme case, the range is entire R2, right? But not always. But as soon as you see 2 by 3, you can think about, well, it takes vectors from R3 and then maps them to R2. First, we want to calculate the null space. The null space, again, is the set of vectors. When we multiply A by those, we get the null vector. So we always start from this constraint that we have in the set. We know that A1, our matrix, times an arbitrary x should give us 0. Now, substitute A and x. We know it's a 3 vector because A is 2 by 3, so x must be 3 by 1, so that the matrix multiplication makes sense. This must be 0. And then you can do the calculation. You actually multiply your matrix by x, and that will give you, as expected, a 2 by 1 vector. Again, 2 by 3, 3 by 1. A times x will be 2 by 1. So now we know that x1 and negative x2 plus x3, this is our vector, equals 0. The condition for two vectors to be equal is that every corresponding, the respective, basically, entries must be the same. Now, if this is 0, every line, every row must be 0. The first one is easy. We see that immediately from here, right? x1 must be 0. But also, we see that negative x2 plus x3 must be 0. This means x2 and x3 must take the same value, such as alpha, whatever that might be. So x2 equals x3 equals alpha. So we know that so we recover the structure of every vector in the null space by carrying out this calculation. So x must be in this form of 0, x1 is 0, and x2 and x3 must be the same, alpha. So every vector in the null space of A1 takes this structure. Therefore, the null space of, you can factor alpha. So the null space of A1 is the set of all vectors like this, alpha times 0, 1, 1, and alpha such that alpha is a real number. All the vectors. Now, how many vectors do you have in this set? Infinite, because alpha can take an infinite number of values. In other words, this 0, 1, 1 gives you one basis for the null space, as we talked previously. And using that basis and all linear combination of it, this is producing the null space for us, which is a subspace. We show it later again. So when you're given a matrix and these smaller scale examples to practice, and you are asked to calculate its null space, this is how you can do it, okay? You could get more vectors, different matrices. Eventually, again, you will use Julia and computer to do that. They will give you the basis. We leave that for the lab to practice with the algorithm. Luke is asking, is it R3 because there are 3 vectors? And is it range R2 because it's... Yes, so because A1 is 2 by 3, it has 3 columns. So every vector, such as x, must be part of R3. And every output, such as y, it must be in R2 because we have 2 rows. So the next example here, we continue. We want to calculate the range of A1. It can be the case that our matrix cannot cover the entire R2, only a subset of it, and that's the range of that particular matrix. And we want to know what is that subset, which later we will show that it's actually a subspace, more than a subset. Another example of a null space first, before we calculate range. So now we want to calculate the null space of an upper triangular matrix. This time our matrix is 3 by 3. It's a function that eats 3 vectors, gives you 3 vectors. Again, the definition, we start from A2 times x must be 0. Therefore, our matrix x1, x2, x3 must be 0. And then we carry out as before, right? So, this is exactly what I wrote. So we want to calculate the null space. A2 times x must be 0. We substitute a and x into the equation. Now, what is the conclusion here? Because A is an upper triangular matrix, we can actually use back substitution to solve this equation. And in particular, there is no zeros on the diagonal of this upper triangular matrix. So starting from the last row, the only explanation for x3 is that it should be 0, right? Now, if x3 is 0, then x2 plus 2x3 implies that x2 is 0, because x3 is already 0. If x3 and x2 are 0, then x1 must be 0. So when it's upper triangular or lower triangular starting with forward substitution, and the right-hand side is 0, the only explanation is that the vector itself is 0. So the null space of A2 is only the 0 vector.
Does that mean that the columns of A2 are purely independent?
Question is, does that mean the columns are linearly independent? Yes. So that's, eventually they all come together. You could use any of the equivalency to say that, right? The null space of A2 being only the 0 vector, that means A2 has linearly independent columns, which we're going to learn a new term. You can call it as a full rank, or matrix. At the end of today's lecture, we're going to use a new terminology. So this null space is zero-dimensional because it has only the zero vector, one element. Every combination of zero is zero again, right? So it's always zero. What about the range of our matrices? We want to find the range of A3 and A4. I think A3 is the same as before, A4 is not. Let's start with A3. We want to calculate the range of our matrix. Now, we start again from the definition. The definition is that the range of a matrix, such as A3, is all the vectors A3 times X, such that X is in R3 because our matrix is 2 by 3. Substitute your matrix and vector. This is what we get. Now, it is common to replace X as variables with alpha to just point out that these are coefficients, real numbers. But it's really just a change of notation. It doesn't change anything. So from these two lines, the only thing I'm doing, I'm changing the variable X to alpha. Just psychologically, we think about it as coefficients. Or coordinates, as we talked last time, right? That we did the same thing. So I'm going to continue with alpha. We know that a matrix times vector can be written as linear combination of its columns. This is the second way of multiplying matrices. And all alpha values are real numbers. Then we also recognize that from the last line in the previous page, that the third vector here is not linearly independent by just looking at it. This is a small example we're practicing, right? By just looking at it, we can tell that this vector is just negative of the second vector here, right? Now, if it's a multiple of another vector, then it's redundant. It does not add anything. You can just combine both of them into one vector. So, if we get rid of the redundant vector, the linearly dependent vector alpha 3, the one that alpha 3 is multiplied by, we get that the range of A3 is alpha 1 times the first column plus alpha 2 times the second column. It is linearly dependent on the second column, right? Because, so if A is here, V1, V2, V3, or A1, A2, A3, V3 is negative of V2. Right. In general, that's the case. That right. Your linearly dependent columns, you can have more, will be dependent on the rest of the columns that are linearly independent. You can say that, right? So this is the range of A. We calculated that. Range of A3 is the set of all linear combination of two first columns of our matrix. What does it mean? That means any vector, such as y, that you multiply A3 by x, belongs to that set. It's not arbitrary. You can write it as a linear combination of these two. Now, of course, the linear combination of these two is going to cover R2 here, right? In fact, the first one is the first canonical basis, and the second one is the negative of that, which doesn't change anything. You can just take the negative of your basis. It's the same thing. What about A4? Another example. Now we have an upper triangular matrix, but this time we have an interesting case that there is a 0 in the diagonal. So as before, start with the definition of the range. Write it down. That means that A4 times any x such that x is in R3, again, because A has 3 columns. So x must be in R3. Substitute A and x, replace x with alpha, write it as a linear combination of the columns of your matrix. And what we will see, we see alpha 1 times column, first column, plus alpha 2 times the second column, plus alpha 3 times the third column. What can we observe here this time? Are they all linearly independent? No, right? Why? Exactly. Luke also mentioned it in the chat. The second column is just twice of the first column. So we can just drop it, because whatever it's giving us, we can generate from the first column by picking a different alpha value. So we drop that, and that's the range of our matrix. What is interesting here? It is different from the previous case, because previous case we had a linear combination of two vectors. It made perfect sense. It covers R2. But right now, these vectors are 3 vectors. However, we have 2 of them. So can we say that it does not cover entire R3? Can I say that? Permission not granted yet. How many bases do we need to cover R3? 3, right? The canonical basis was the columns of 3 by 3 identity matrix. We need 3. With 2 of them, at best, we can cover a plane. There's going to be one direction that we can't move. Now, the plane can be any crazy shape. It doesn't have to be perfectly like XY plane, YZ plane. It can be oriented. But with 2 vectors, we're just going to span a plane. So it is interesting that even though our matrix is 3 by 3, it takes vectors from R3 and then maps them to a plane. And the reason for that, we know that because, well, we had 2 linearly dependent columns, and with this 0 and this upper diagonal matrix, it reveals this structure that you can guess that this is probably the reason. So matrices do not need to cover the entire vector space. Like if it's 3 by 3, it maps to R3. It doesn't need to cover entire R3, right? That depends what's the actual numeric values in the matrix. Yes, the range is a subset of R n number of rows. Because A in general is n by m, right? Maps from Rm to Rn. The range at most is going to be Rn, but can be a subset of Rn. But it's more than that. Now we're going to see. It's a subspace. It's closed. But it's correct to say it's a subset of Rn. But we use more special name, right? If it has more features, we use more special name to highlight that, well, it's not just a subset, it's a subspace. Because all subspaces are subsets, but not all subsets are subspaces. So now if you're given a small matrix, you're asked to calculate this null space and range, you can do it like this, right? Obviously, if the matrix is large, we need an algorithm to do it. That's not how we're going to do it. I'm not covering the algorithm in the lecture. There is a method based on QR factorization. We can cover all the bases for the null space of a matrix. That's a good topic for the lab to talk about the algorithm. And you can read it in the book. And then when you use null function to get the null space, you get the basis of the null space back. You don't see the alpha values. Yes, so more on calculating null space with Gram-Schmidt, another utility of Gram-Schmidt and QR in the lab. Now, you probably guessed this. Let's formally talk about it. Range of A equals column span of A. Because if the range of A ends up being whatever it is, linear combination of the columns of A, and if there is any dependent column, we drop it because it doesn't add anything. So essentially, range of A is the column span of A. And the span was all possible linear combinations of a set of vectors. So let A be again our n by m matrix. We have m columns. It is equivalent to say that range of A equals the set that A times X, such that X is in Rm, equals the span of the columns of A, or the column span of A. So these are exactly the same thing. Again, as a reminder, a span of a set of vectors was a set of all possible linear combinations of them. Okay, does this make sense to everybody? I'm just highlighting here that span is all linear combinations. It's the set of all linear combination of the columns of A. Okay, now we want to show something that promotes two important subsets, null space and range of a matrix A, to a subspace. So they're not just subset, they're subspaces. First, we want to show that the null space is a subspace, and then we want to show that the range is also a subspace. Let's start from the first one. Now, to show that, we assume that we have two vectors that belong to the null space of A. By definition, if these two vectors are in the null space, then they must satisfy A times V1 equals 0 and A times V2 equals 0. So V1 and V2 are arbitrary vectors. We do not specify any values, but they belong to the null space of A. To show a set is a subspace, we need to show that it's closed under linear combination. That means every possible linear combinations of V1 and V2 also needs to be in the null space of A. Then in that case, we can say the null space is closed, therefore is a subspace. And to show that, we need to just directly multiply. You can consider V3 to be a new vector, or I'm just going to use Y, a new vector like this, right? Then if A is also in the null space, then A times Y must be 0. And that means A times alpha 1 V1 plus alpha 2 V2 equals 0. So you see, we start from here. A times the linear combination of V1 and V2 must be 0. Matrix multiplication is distributive. We distribute A over alpha V1 and alpha 2 V2. Alpha is a scalar, we can move it to the left. Then we recognize that, well, by definition, these two terms are 0 because they belong to the null space of A. And 0 plus 0 gives us 0. So this proves that no matter what, if you have two vectors in the null space and linearly combine them, the results will be in the null space. Why? Because it satisfies the constraint. So, the conclusion here is that the null space is closed under linear combinations, and it is therefore a subspace. So the steps, again, very important. Start from the definition, use properties or constraints that you're given. For this particular case, we want to show it's a subspace. We see if it satisfies the constraint. Let's see how we can prove the second one. We want to show that range is also a subspace. That means that if you pick two arbitrary vectors, V1 and V2, in range of A, then there must be two other vectors, U1 and U2, in the domain that when you multiply A by U1, you get V1, right? There's got to be some vector that gives you V1 because V1 is in the range of A. Again, A n by m maps from Rm to Rn, and I'm telling you more precisely range of A because we just learned that the range of A is not necessarily the entire Rn. So it's more precise to just talk about the range of A. So if I tell you that V1 and V2 belong, they're in range of A, then there must be some U1 and U2 in Rm such that A times U1 gives me V1 and A times U2 gives me V2. Because U1 and U2 can be any vector in Rm. There is no constraint on these vectors. There's got to be two vectors to produce U1 and V1 and V2. Okay, as before, now let's form a linear combination of V1 and V2 and check if it's the result, if the result is in range of A, because that will show that the range is closed under linear combination. To do that, we form the linear combination of V1 and V2. Now, there's got to be a U that gives us that. We don't know what. So sometimes in life, you just need to get lucky. Just working hard is not enough. A lot of time you should get lucky. More than you need to work hard. Here, we're just feeling lucky today, and we're going to try. It's OK to try, and if it works, then that's true. So we propose to try alpha 1 plus alpha 1 times U1 plus alpha 2 U2. It's a reasonable guess, right? We guess that the linear combination of U1 and U2 might produce that outcome. And we try. So A times U, we propose U to be linear combination of U1 and U2 with the same alpha values. Matrix multiplication is distributive. We can shift the scalars to the left. This is a typo. This should be U2. Okay? Then we know that from here, from the beginning, we know that this is V1. This is V2. So it works. Our guess was correct. And with a lot of luck, we just proved that the range of A is also subspace. But then we have survival bias. We say that. We proved it because we're good at linear algebra. But that was an educated guess also because it is linear, so we could guess that linearity should help us to preserve that linear combination. So the conclusion is the same. It is closed under linear combination. Hence, it's a subspace. So both null space and range of A are subspaces. They are closed under linear combination. Do you have any question so far for? Okay, your question is, how does this line prove what we're after? Do you agree that if the range is closed under linear combinations, then alpha times v1 plus alpha 2 times v2 must be in the range, right? So it's in the right-hand side. Just like here, then I said, if v1 and v2 are in the range of A, then there's got to be some equivalent vector in the domain, u1 and u2. Now, in this case, I am also claiming that there's got to be a u. I don't know what it is. But if it's true that the linear combination is in the range, there must be a u vector that will produce that. Now, infinite possibilities, we just made a guess. Our guess is that we propose to try it, right? You may try 10 things and then say, you might say that, how about alpha 1, u1 minus u2? I don't know. Try this guess. Probably doesn't work. We did the guessing part for you last year. So this is just a proposed solution, right? Now, it's proposed. When you check the equation, if it works, then that proves. There's no need to go back and be worried about u, because we found that u that will produce this. And that's basically linear combinations of u1 and u2 here. In fact, does produce linear combinations of the output in the range.
Would it be correct to think of this not as a, or like a check, like if this is true with a certain combination of vectors, then it is a subspace?
Can you repeat it? Is it true if we say, if? Is it true to say that instead of proof, this is just a check, a verification? You can't say that, but it proves it, because we just proved that every arbitrary vectors that you pick, if they're for their linear combinations in the range, right, there is a vector in the domain, and that's the linear combinations of their respective vectors in the domain. That's the proof. It is a verification, this line, but also proves that.
So we're taking AU from the range and saying that that's...
Mm-hmm. Yeah, we propose to be a solution, right? I give you an equation, and I'll ask you to find its solution. You say that I'm going to do it by guess. You try numbers, and it works. If it satisfies, that is a solution, right? Regardless of where you got that. For example, f of x equals x squared minus 1 equals 0. Now, I'm going to tell you that what is the value of x that satisfies this equation? Where did you get plus minus 1? Plus minus 1, right. But where did you get it? Now, you might say that, oh, I have the scales. I'm going to move 1 to the other side. I'm going to take the square root. I know it's going to be plus minus 1. Another person, Audrey, says that, well, how about we try plus minus 1? And we try, and it works. And is she wrong? Absolutely not. As long as it works. So that's basically what we did, right? I understand your frustration. We took a lazy path, but that's perfectly fine to prove something. Okay? You could take a longer path, but you would hate me for spending 1 hour. Now, this is a fundamental property of a linear map, linear function. Linear functions preserve this. I could tell you that, well, A is a linear map. A property of linear map is to preserve the linearity. By definition, a linear map preserves the linear combination. Therefore, the equivalence U must be in the form of a linear combinations of U1 and U2. And then we tried it, and it works, right? We could go from more formal way and make a story around it. But ultimately, that's just an easy way to prove it.
So we're just picking a random AU value, saying, oh, there's a U in the domain which satisfies this.
Yeah, that's what we did here. I appreciate you being rigorous, but that's also fine. We're just being smart. It's not always about working hard. Okay, so now in a course on linear systems theory, this type of thing will show up. You see that this is a property of linear maps and linear systems. That the output, the range, is a product as a linear combination, right? It is a linear combination of a bunch of inputs. That's also called superposition that I mentioned it early on in the course. It's called superposition. That's what makes nonlinear systems strange to work with, because the linear combinations of input will not produce linear combinations of output. The change is not linear, and therefore it's hard to predict what will happen. All right, we move on to relation of null space and range. We want to link it to the solutions of linear equations. Suppose A is n by m. We have a system of linear equations in matrix form. And we know null space of A and range of A. We want to see how they are connected. The first connection is that if AX equals B has a solution, then, it has a solution if and only if the right-hand side B is in range of A. Now, this is not new. We already talked about it, that B must be the linear combinations of the columns of A. Therefore, it's in the column span of A. Otherwise, it is not possible to produce B using this equation.
Would it be equivalent to say that if B is in the range of A, then AX is equal to B times solution?
Yes. It's if and only if, right? So if and only if means both ways. So it's not new, but we're using a more maybe sophisticated way of saying that. X equals B has a solution if and only if B is in range of A. The second connection is that if AX equals B has a solution, then it is unique if and only if the null space of A is the zero vector. You might remember this as the property that the determinant of A transpose A is not zero, or the columns of A are linearly independent. All of that means that the null space is the zero vector, right? So AX equals B has a solution, we know it's unique if the null space is the 0 vector. Now, suppose we know a solution of our system of linear equations, x tilde, let's call it a solution. If it's a solution, that means A times x tilde equals B holds. Then the set of all solutions is, of course, all x vectors such that Ax equals B is satisfied. But also you can say that A is basically that solution, x tilde, plus the null space of A. Or you could put it in one set and say x hat such that x hat is one particular solution right? This is a particular solution of the system of linear equations plus eta, it's a Greek letter. You can use other letters too. This is called homogeneous equation, solution. So the solution of linear system of equations is always the sum of a particular solution and a homogeneous equation solution. That's basically Ax equals B 0, right? Why? Because we know that if you have this form, right, we get A times X. We distribute A, and we get A, eta, plus 0, because this is in the null space of A. No matter what you add here, it will be 0, and this is B. So when you have a particular solution, which comes from B, now it's particular because it comes from a particular B. That B, whatever it is, it will give you x tilde. When you have a particular solution, you can always add every vector from the null space to that solution, and it will not change that. So your set of all solution is actually sum of both of them. Now, of course, the null space can be only the 0 vector, but we know that that's not always the case. Right? So this vector eta can be only 0 if the columns of A are linearly independent, but it's not always the case. It can be non-zero too. This is strange, because you have a particular solution, you can add. Because if the null space is not just a 0 vector, you have a basis and you have infinite number of vectors. So your set of all solution has infinite number of solutions, elements. So you can take your particular solution and then imagine a knob. You can tune that and they can change it to many vectors picking from the null space. It changes the value because you get an x hat that is different. Yet the right-hand side doesn't change. That can be desired, that can be disastrous, because if it's a physical system, maybe that leads to explosion. You don't know what's entering your system. You're not going to know because from the outcome that you observe, you don't see it. You only observe B. And again, in a linear systems theory, in control theory, they talk about observability. This leads to issues that something is wrong, but you're not going to be able to observe that, and that's very dangerous. So We leave this out for your future courses. But it comes from linear algebra again. All the tools that they use, we have here. The fourth property is that AX equals B has a unique solution if and only if B. Basically, this is summarizing all the previous steps, right? AX equals B has a unique solution if and only if, first of all, B is in range of A. And the second is the null space is the zero vector. Well, that means that based on what we learned so far, this is a fancy way of saying B is linear combinations of the columns of A, and determinant of A transpose A is not zero, or the columns of A are linearly independent. This is a more compact way of writing it. B is in range of A, and the null space of A is the zero vector. The fifth one is saying if B equals 0, it's always true that B is in range of A. Why? Because the homogeneous set of equation always has the trivial solution. Because the null space at the minimum has one element, and that's the trivial solution. Zero vector. And that goes back, it's both ways, that if the null space is a zero vector, then A times X equals 0 has a unique solution. You also know that the range of A is a subspace. Subspaces always contain the zero vector. So even if B is 0, it must be in the range, because range is a subspace. Too many equivalency to iterate, but that's good, because that shows consistency. It might be confusing, but once you internalize them, then they all mean the same thing. And the fancier it gets, the less text we use. We use universal mathematical symbols. No need to speak English. And some people use that to say mathematics is a democratic field. It is not true, of course, but the part that the symbolic calculation is universal, people can do it in Russia and we still understand what they solve. That part of it is great. Because we get a lot of results from Russia in mathematics. That's why I named that particular country. Rank, the last topic of today is rank and nullity. This is going to lead to the fundamental theorem of linear algebra. And that's how we're going to end chapter 10. We're going to define a new term, rank. What is the rank of a matrix? For an n by m matrix, the rank of A is simply the dimension of range of A. And you know from last lecture that dimension of subspace is the set of it's the set of bases, right? Linearly independent bases that we have. So when you calculated range of for example, A, in one example, you got 2 vectors, then we knew that the dimension is 2, then the rank of that was 2. We're going to see an example. Also, I like this way of thinking about it. Rank of a matrix is the biggest determinant that you can find inside that matrix that gives you non-zero value. Let's say I have a matrix of now I'm not looking for any particular calculation, but this is the 2 by 3 matrix. Determinants also only defined for square matrices. So you can search for this determinant, right? Or you can search for this one. So you cannot have a 3 by 3 determinant here. So you already know that the maximum rank here is 2. You should always go with the lower number, right? So if any of these 2 determinants is non-zero, then the rank is 2. That's also a quick and dirty way to check. You don't need to do any other things. Just to connect it with determinants, you can also visually look at it. Think about it this way. But we're going to use something else. So the second topic is nullity. Nullity is the dimension of the null space, right? So rank is the dimension of range. Nullity is the dimension of null space. And because the range of A is always a subset of Rn, right? A is a map from Rm to Rn. So range of A is always a subset of Rn. So the rank is always less than or equal to n. It cannot be bigger than n. It's the same reason, right? For R3, you cannot have 4 bases. Maximum number of bases that covers the whole space is 3. Okay, rank nullity theorem. The fundamental theorem in linear algebra says that it has a name. It's called rank nullity theorem. It says that for an n by m matrix, the sum of its rank and nullity equals equals m, the number of columns of the matrix. So if you know the dimension of its range, its rank, you can already recover what is the dimension of its null space. That's interesting. If you know one, you can recover the other one, because they should, the sum of them equals the number of columns of our matrix. So rank is essentially the same as the number of linearly independent columns of A, okay? Because it's the dimension of the range of our matrix. Then it follows that the nullity is basically counting the number of linearly dependent columns. So you can read this as the sum of linearly independent vectors plus the sum of the number of linearly independent vectors plus the sum of the number of linearly dependent vectors equals total number of columns of our matrix. That's what it means. So rank, number of linearly independent, nullity, counting the number of linearly dependent. So what happens if all the columns are linearly independent? Yes, the null space, we know that it will be the zero vector, all the stories we talked about, the solution will be unique, and all of that. So that when the null space is only the zero vector, it is basically zero dimensional, right? This is the same thing as real line, right? It is one dimensional, but zero itself, it doesn't have a dimension. A point doesn't have a dimension, right? You need an infinite number of elements. You need a span to add a dimension. So when the null space is the zero vector, it is zero dimensional. Therefore, rank will be m, and then nullity will be 0. Now, to save you from trouble, we're not going to go through the proof, but the proof, please take a look and ask your questions. Office hours or Piazza. The proof is in chapter 10.6 of the book. But hopefully this is a very intuitive theorem. It makes sense, right? Sum of the number of linearly independent plus the number of linearly dependent should be at most the total number of columns we have. It cannot be more than that. Or it cannot be less than that. Let's verify this theorem. It's always good when you learn a theorem and it's abstract, try to verify it numerically. It helps a lot to actually learn it. And if it doesn't work numerically, either the theorem is wrong or your numerical calculation is wrong. Now, if the theorem is well established, probably you want to doubt your numerical example. If you just prove the theorem, you're in trouble. Both of them could be wrong. We have A3 and A4 from our previous examples. We want to verify rank nullity theorem. We have already calculated the rank and nullity of A3. So the rank of A3 is 2. The nullity, this is from our previous examples. If you go back, is 1. And some of them is 3. And A3 was a 2x3 matrix. We can see that for a 2x3 matrix, the sum of its rank and nullity equals 3. For A4 is 3x3 matrix. Now, using that trick that I told you, I can already see here that this determinant is non-zero. It's 2x2. So the minimum rank will be 2, right? The 3x3 determinant will be 0 because we can see that 2 columns are linearly dependent. So the rank is 2. And then when you calculate the null space, it gives you 1 vector. The span of that vector is the null space. So the nullity, which is the dimension of null space, is 1. And sum of them, again, is 3.
I'm a little confused on that determinant trick that you're talking about, because can't you take the determinant of 3x3?
We can. I was just saying that in this case, it will be 0.
Okay. I guess I'm just like a little confused when you do like the trick of like you use the number of determinants that you can get by the 2x2s to then get.
It's the biggest determinant is only defined for the square matrices, right?
Yeah.
The biggest determinant that you find here in this matrix that is non-zero, that size is the rank of your matrix, right? Now, I don't even remember the 3x3 formula. But if you calculate it, definitely it's going to be 0 because we see one column is a multiple of the other column, right? It will be 0. Check that. So our next best chance is finding a 2 by 2, right? And I can already see this 2 by 2 is going to be 4 minus 0, 4, non-zero. And this is 2 by 2, so the rank is 2. This is good for small matrices. We can quickly verify. Of course, it's very painful to look into determinant of big matrices. So we have verified the theorem. This is the end of the lecture and chapter 10. We've come a long way. We've finished 10 chapters of the book. And that's pretty much the linear algebra part, because we're going to have a change of gears. You will have projects and homeworks and lab still. But from chapter 11, we're going to talk about a little about root finding, optimization, which eventually will lead to some exciting topics on machine learning, edge detection. You'll see how all of them will get connected to linear algebra. We can run a convolution, 2D convolution on an image by just algebraic manipulation, and you get edges of a person, for example, out of an image. So, because we covered a lot, next Monday we're going to have a recap, right? I'll make a lecture that put everything together, all the 15 lectures in one lecture, right? It's going to be a 24 hours lecture. No, it's going to be 1.5, same time. That's my challenge. I'll drop what I must. So we want to reiterate and go back to the cases of solutions of linear systems, and then now we're free to use the latest terminology we learned, right? We can connect it to the null space, span, and all the fancy terms that we learned. But congratulations on continuing and finishing 10 chapters of the book. We're done with the lecture. Do you have any questions for today?
I'm sorry, I'm still a little confused on the determinant, because like when
Okay.
you go to try to find like the max determinant of that one, isn't it 4 of the upper right, not 2?
Yeah, this one here, right?
Yeah.
The question is still about this determinant trick. It is 4. But it's non-zero, right? Whatever it is.
Oh, so it's the number of non.
Yes, it is 2 by 2. So the dimension of it will be the rank.
Okay.
Right? Yeah, I might have confused you by this 4. As long as it's non-zero, that means that the rank is this dimension 2.
Okay.
Yeah.
You use the maximum determinant, like you use the determinant.
Biggest, right. Biggest one that I can find is non-zero. Because now we need to calculate it, but here I know that 3 by 3 is 0. I know that determinant of A4 is 0. Because the second column is twice of the first column. Well, that's the end of the lecture. I'll see you on Monday. And you have a homework due on Thursday. Some of the questions are related to calculating the null space. So today's lecture, make sure you apply what we talked about to those questions.